Fourier Transform works on a combination of constructive and destructive interference. So it collects everything in the time domain in time, and then converts it to the frequency domain, so to something that looks more like a spectrum that we're used to. So if you have two waves of a monochromatic light source that are in a phase, they're going to constructively interfere and they'll increase amplitude. If they're exactly out of phase, they're going to counteract each other and they'll end up making destructive interference or cancelling each other out. So that's kind of the basis of Fourier transform. The advantage is that you can take a spectrum very quickly, take lots of them and signal average to get a better signal to noise ratio. You also can allow lots of light through. Since you're collecting the time domain, you don't have to have a narrow slit anymore. So again, that improves the signal to noise ratio. We're going to start off by saying that this moving mirror is in the position so that this distance between the beam splitter and the fixed mirror is the same as the distance between the beam splitter and the moving mirror. And we'll start with just a simple monochromatic light source, so a single wavelength. When it gets to the beam splitter, half of this wave intensity is going to be sent to the moving mirror and half to the fixed mirror. So half is reflected and half is transmitted. So half of it will go to the moving mirror and half of it will go to the fixed mirror. Because it's the same distance, these will hit at the same point and they will be reflected in phase. And again, when they get to beam splitter, half the radiation will be transmitted, half reflected, so they recombine. And what's going to happen is they're going to recombine in phase. And that's going to give us constructive interference. Now imagine the same case where we're dealing with a light source and the mirror has moved. We're going to say it's now moved a distance of a quarter of a wavelength. Now when we have our wavelength again, going to strike the beam splitter, half is transmitted, half is reflected, but now it's gone an extra quarter of a wavelength to get to the moving mirror compared to the fixed mirror. So when they're reflected, they're actually going to be out of phase. Since this is the quarter wavelength, it's going to take a quarter of a wavelength extra to get to the mirror. Oops, I didn't draw that the whole way. And an extra quarter of a wavelength to travel from the mirror back again. So it's actually a half wavelength difference. So this is going to be exactly out of phase with the wave that comes from the fixed mirror. So when they recombine, they're going to be exactly out of phase and we get destructive interference. For a single wavelength, if we plot intensity against time, then there will be periods where the two waves are in phase and it's constructive, and exactly out of phase, so it's going to be destructive. So you get something that looks like a sine wave. The mathematical function, the Fourier transform, will recognize that frequency. So it can convert from the time domain to the frequency domain. If you get two waves, then in time, in the time domain, they're going to interfere with each other, and you get something which in the musical world is known as beats, where you get alternating loud and soft. And again, not drawn very well, but Fourier transform can recognize that as two frequencies. And obviously if you get lots of wavelengths joining together, you're going to end up with basically just a mess. In the time domain, something that we can't make any sense out of, But mathematically, again, we can convert that to the frequency domain and get something that looks like a spectrum.